overview, and you need to have also an overview on the well inflow performance, which we will already review today, and outflow performance, dynamics, the reservoir fluid properties, and the reservoir properties. That is what you need to know before starting the session. If we review our fundamentals, a new well which is drilled normally have the capability to flow naturally. That means that this well will have the capability to overcome the gravity of the well fluids inside the well and deliver the well fluids to the surface with a certain pressure that will be capable to push these fluids to our facility, which we call the wellhead flowing pressure or the wellhead back pressure. So most of the modeling today is done through the well modeling softwares, and sometimes it's done by hand just for illustration. What we do with our well models, so normally in oil field, there's some wells connected together network. All of them produce to a oil production facility, and these wells together form a network model. Each of them will affect each other by the back pressure, which is proportional to its flow rate and the pressures. This means that before putting a new well onto the network, we need to model it and model its effect on the other wells. Fortunately, the PIPESIM as a software, it can model both the network and well model. Our focus today will be on the well model only. So in order to understand the well performance, this is a simple schematic illustration for this small guy running the street with a certain length to reach the entrance for his building and go upstairs 10 floors. So as this guy runs the street, he will lose some of will reach the entrance with a certain energy. The energy he loses will be proportional to his speed. While this guy is trying to go flat, he will require a certain pressure. This pressure will also be proportional to the speed of running up the stairs. And if we need to take a solution point or a nodal analysis point at the entrance, so the available power with this guy after he runs the street and reaches the entrance as the or the available power. And this available power need to overcome the required power to go up the stairs. So going up the stairs will need with a specific speed will require a specific amount of power, which we call the required power, and the guy will reach the entrance with a certain amount of power, which we call the available power. So in order to this, the available power need to be the same like the required power. Let's do this analog on our well. So while the reservoir fluid moves inside the reservoir with a certain drainage radius, RE, and the reservoir has a certain pressure or reservoir with a certain height and certain radius till it reach the bottom hole with an available pressure, which is the pressure. Then this fluid will need to go up the tubing capable to deliver this fluid to through the surface lines to the facility. describe flow performance relationship, which describes the fluid flow inside the reservoir. And we describe the vertical lift performance, describing the upward flow of the fluids inside the tubing. The intersection of both will give us the operating point, which is the capability of the well to flow naturally at a certain wellhead flowing pressure. To dig deep in this one, this is our reservoir performance relationship, how it looks like. So as the bottom hole flowing pressure increase, the flow rate decrease and vice versa. So this is how it looks like, the reservoir performance relationship or the inflow performance relationship, and we can represent it in a simple way, which is a straight line IPR or a constant productivity index IPR, or with a Vogel correlation where the curve, the straight line will start to deviate at this red bar. The start of this deflection is called our bubble point pressure. So this is how we describe our reservoir performance. The reservoir performance will mainly depend on the fluid properties, which is mainly the viscosity and beta O, the formation volume factor for the oil, and the rock properties. The rock properties will be mainly about the permeability and the height of the reservoir. Another two factors will be the drainage radius and the well radius, which will represent the distance the fluid will travel at the reservoir. So if we look at the equation on the left above, the flow rate for each reservoir and fluid will be equals a constant multiplied by a delta P, which is the reservoir pressure minus the bottom hole flowing pressure. So it's clear from here that at a lower flowing pressure, the reservoir will give more fluids. So if we get this constant and call it a productivity index, we get the equation that we have here. The flow rate Q will be equal to the productivity index multiplied reservoir pressure minus the bottom hole flowing pressure, which is the delta P. So any flow across any porous media, it will be depending on the characteristics of this media. And so if we draw this equation, at each flow rate, we get the bottom hole flowing pressure. We draw a straight line for simplicity. And this is the inflow performance relationship. Will be depending on the K, which is our permeability, the H, which is the reservoir, the skin, which we will assume 0 in our exercise, and the reservoir fluid properties, mainly the formation volume factors and the viscosities. This is a Vogel correlation to describe flow of fluid inside the reservoir for a fluid flowing at a pressure below the bubble point, and this is Q over Q max equals 1 minus 0.2 multiplied by PWF over PR, and we subtract 0.8 multiplied by PWF over PR square to 2. Equation I suppose most of us are familiar with. And the other curve that we need to be familiar with is the vertical lift performance. Here, another criteria for the vertical lift, as the bottom hole flowing can deliver the fluid with a higher rate, or as we request a higher rate, we require a higher pressure at the bottom hole to deliver this higher rate. So if we do it, we have the rate increasing and the bottom hole flowing the pressure And parameters that will affect this outflow performance will be the fluid type as well, which is the viscosity, the gravities of the fluid, the temperature and pressure, the conditions at each point, and the tubing size and the friction coefficient. So as the fluids travel through the tubing, it will face some frictions. It needs to overcome the gravity of the hydrostatic pressure, and it needs also to deliver the fluids up to the surface with a certain amount of pressure, which is the back pressure to the well. How the software do this vertical lift performance? We give the software the main parameters for the correlation, the vertical lift performance correlations, and the software uses these parameters to predict the densities, the viscosities, and all the fluid properties at each step. It do it as steps going upward. At each step, it calculates the new temperature, the new pressure, the viscosity, the specific gravity, and the gas properties, and so on, till it reaches the calculation to the surface. So the vertical lift performance, and on the left, the inflow performance of the reservoir, and each of them will depend on certain parameters of the reservoir, fluids, and the well construction. The intersection of both will be the flow rate. If we have more back pressure, sometimes this intersection is not existing, like the well we see on the right. If we have increase in the back pressure, the vertical lift performance will shift upward and there is no intersection. If the reservoir pressure depletes, have a decrease, we will have a decrease and the inflow performance and it may not intersect, and so on. So some dead wells is due to the back pressure, so you cannot produce to the facility, but you can produce to the atmosphere. Some wells are dead due to pressure, and so let's go on to our main focus today is PIPESIM model, which is able to model both the well and the well and the network models. So we have our exercise, a new well drilled called well 1-1 drilled, and it reached TD of 3,100 meters, and the well was logged a reservoir which from the geological model we know its drainage radius is 1,000 meters, and the reservoir contains a pure oil from the sample we take during the logging, and the top of this reservoir is at 2,930, which we see on the log at the right hand side. We do the RDT log, and from the RDT we have the reservoir, the fluid mobility, we have 15.7 mobility, and pressure almost 4,360. The downhole temperature from the RDT log also is 220, and from offset wells which we produce from the same reservoir, we have the viscosity is 0.6 centibars from the produced fluid. The API is 30 API degree, and the gas oil ratio for the fluids is 386 scaf, which is a standard cubic feet per barrel. And from the open hole log also we found that the thickness of this sand is only 3 meters thick. And for network, we know that the well will produce against a back pressure of 250 solid pressure. So decision taking based on the model to run the liner and produce this interval, and it is required to know how much flow rate will be we will get from this interval. So one point here that we need to To mention also in the nodal analysis that due to the why the well will flow at the intersection point, this is due to the constant of mass flow rate. So the Q here is standard condition. The volumetric flow rate at the standard condition will be constant as the mass flow rate will be constant due to the low conservation of mass. Let's start our exercise, and I will share with you now the model. Here how our interface for the PIPESIM will look like. Let's start by clicking workspace and select a new well. So there's two sections here. The first one is related to the network modeling, and the other section will be about well modeling. So let's start a new well model. So this is a blank page for the well model. We will go through the sections one by one for these tabs. First one here, we have a general data about the well. We will call the well 1-1. And here is a well type, either it's producing well fluids or injecting well fluids. And this is all about the general data. The second tab will be the tubulars, which we will describe here the downhole construction of the well casing and tubing and depths of each. Then the deviation survey, which will describe the well trajectory, either it's vertical or deviated. So for the deviated wells, we can represent it as a 2D representation or a 3D representation. So here we will represent it as a vertical well, but by entering the deviation survey data. So for a vertical well, the measured depth will be the same as the TVD, and the TD will be the same as the measured depth also for the TD. So this is a vertical well. We can simply choose a vertical well from here. Downhole equipment we will see during our modeling. Then we have the artificial lift. So the artificial lift tab, we will be capable to model the artificial lift of ESP, PCP, gas lift, and design them as well. Then the heat transfer, which will affect the heat transfer between the fluids as it travels up the well, it will lose some of the heat of this fluid into the well. So the steady state temperature for the fluid at its flow up the well at coefficient as 8 for oil well and as 3 for gas wells. Soil temperature at wellhead is the ambient temperature, which is here in Egypt about 80. In the next section will be the completion section, which will describe the reservoir. Let's start. If we look at our example, we have a new well, and I'll start now constructing the well schematic. Here we see on the upper ribbons, we have the case stuff. We can have two options to represent the well, either by just clicking on the casing and dragging it on the well schematic. Then we enter the description here, or just if I delete it back, we just click add and add whatever to represent the schematic, either the simple way or the detailed way. The detailed way will show us tubing and casing, and the simple way will be all in one. It is not reversible. From detail, you cannot reverse this action. Let's start our well. Modeling our well, we have the 958-inch casing. Here I drag and I will start the actual depths of section name. I can name it whatever I want. Let's name it surface casing. And here for the casing, it's from zero. It's not a liner, it's a casing. From zero is 2,600 meters. The ID is here written down, but we will get our casing from the database by clicking the three horizontal points. So our surface casing is 958 in whatever column you need to search about it. So the OD for the 958-inch casing is 9.625. We will choose our casing, which is already actual. I click the casing and click OK. It starts to appear here. Then another row is added by clicking this plus. I'll choose our liner, which will start from 2,500 between the previous casing and the new liner. This is for the sake of the well integrity. So the new liner will be from the 2,500 meters down to the well TD, which is 3,100 meters. Here, if I look at this ID, I'm not satisfied because it's on in my well. I will click the 3 points. My casing from here. It's an L80, which is the grade. All details for each casing is here from the database. So I'll choose my liner, which is the drilling team has run, and on our schematic on the. Now I'll drag the tubing here. Okay, so I'll drag the tubing. Same. I'll the depth of the tubing end will be above. Normally we above 30 meters. So the top of the reservoir from the log is 2,930. I'll put the end of my tubing at 2,900 meters. And again, I will choose my tubing from the database. I click the three and enter tubing as was run on the drilling rig or the workover rig. I choose it with the material and the specs. I make sure that this is my tubing with the required specs and click OK. Here is my tubing. Here is my liner. We need to block the flow path from the perforations into the well tubing to casing annulus. So we put the bucket again 30 meters above the tubing end, which give us 2,870 meters. So we have completed doing our schematic for our sample wells, which is the fourth tab here. Go artificial lift. We don't need the heat transfer coefficient describes transfer between the well and the fluids, and the soil temperature is 80, as we said. Now the most important part is the reservoir modeling. Now I need to model my reservoir in flow. I click on the completion tab and choose the plus button. I will name my completion here as formation 1. It's a vertical one, single entry point. Here I will put the mid of my perforation depth, which is the perforation is at 2,930, and it's a 3 meters, so the middle of it is 2,931.5 from the data I got already. So mentioning the data here, so for all modeling exercises, rubbish in is rubbish out. So we need to make sure that the input data is QC'd. We make the whole quality check exercise and from where our data is coming from to make sure that the output of the model will be okay. Now, I put the reservoir started to appear on the left side here as these black triangles, and it's named formation 1, but the reservoir properties. So according to my available data, I will choose the IPR model that will represent my reservoir inflow performance. So a variety of options are available here, either by directly entering the well productivity index if I have it from a test on an offset well or for the same well. But here we are speaking about a new well and all the data available is the logging data. So we will choose the Darcy equation which we have already discussed. So the reservoir pressure, as we said, was 4,360 psi. The reservoir temperature from the RBT was 220 degrees Fahrenheit. And here we are speaking about a liquid or oil reservoir, not a gas reservoir. So we'll check here. And using the Google correlation below the bubble point, I can take it or leave it. The reservoir section, for the reservoir thickness, we have 3 meters from the open hole log. The borehole diameter is already the bit diameter by which I drilled the reservoir. So it's 8.5 open hole where we run 7-inch line. The reservoir permeability is simply taken from our exercise. So if you remember that the mobility from the RDT was 15.7, and from the offset well, the viscosity of the fluid is 0.6. So 15.7 multiplied by 0.6 because my mobility is permeability over the viscosity. So if I multiply the mobility by the viscosity, I get the permeability of the reservoir, which will give us 9.4 millidarcy. The drainage radius from the geologist and the reservoir engineer, he said it's 1,000 meters. And here we are done with the reservoir rock properties. Now the skin factor, for the simplicity, we will do it as 0, but for the sake of work, we calculated which will be according to the reservoir, the perforation for the reservoir well interface, how I perforated my reservoir, the damage, the invasion of the mud into the reservoir, and it can be calculated by PIPESIM also. And another option here is the perforation design, which can be designed through the PIPESIM. All these data from here, if you see perforation design, ESP design, and all this stuff. So I can already calculate my skin, and I can already design my perforation, which will give me the minimum skin. So this is for the completion. One missing point is the fluid properties. Okay, the fluid properties, I have here to click the new button, and there is some sample fluid properties: dry gas, light oil plus gas, heavy oil plus gas, dead oil. Here for my reservoir, I will select light oil plus gas and click OK. Anyway, I will put my parameters, and the exercise said that we have a pure oil, so the water cut or the percentage of the water volume of the produced or the reservoir fluid is 0. The gas oil ratio is 386 from the test on an offset well producing from the same reservoir, and the gas gravity from the same source will be 0.8, and the API as illustrated in the example 33.86. So this data, how the model will use it, these data are the input data for the BVT correlation that the model will use it in mainly in vertical lift performance, but also in the IPR or the inflow performance. And I can use and choose this correlation, which correlation I use for this correlation. So we leave, for the sake of time, we'll leave the standard correlations here and click close. And now our model is ready. If we have any problem with our input data, if you see here where my mouse arrow is pointing, this validation will be in red if any data is missing. For example, if I clear this one, I have one validation here. If I click it, it say you go there. The value of the property must be specified. What property? As the well 1-1 completion formation 1. So I click here, it directs me straight forward to the input data error. Now I start to see my reservoir. Here I see on the intersection with the y-axis my reservoir static pressure 4,360, and on the x-axis the intersection is 300, and I may say 380. This is my absolute open flow, or it's a theoretical term, which is the maximum or the Q max that the well can deliver. Here I can tick this point where the model uses a bubble point, the flow below the bubble point with Vogel correlation or with a simple straight line. The most accurate is the Vogel correlation. If I'm sure with my input data for the bubble point pressure and the BVT data. Now we are finished with our model input data. Let's see what data the model can give us. Now I go to home and select nodal analysis, which is the main focus of our exercise, and the model asks me here where the node is. So I choose the wellhead only when I have one curve representing both the reservoir and the well. By drawing the wellhead and the flow rate, which is not our focus now, I will solve my node at the bottom hole. So the wellhead will have the solution point here at the wellhead, and the rate will be the cross section between the surface flow curve and the wellhead flow curve. I choose OK. Now, after choosing, I'll come back to this one. I'll close this window. I'll come back to this one because I believe it didn't appear very well on the screen. I close the window. I go to home, nodal analysis, go straight forward to the window for the nodal analysis. After putting the node at the interface between the reservoir and the well, as we see this ball here, nodal analysis NA. A last input will be our wellhead flowing pressure or back pressure at the surface. Shwamsh Assam, you see my screen?
Yes, Engineer Abdullah.
The nodal analysis is appearing in your PC?
The software one, the PIPESIM.
Okay, so I believe this window didn't appear. So
Okay. So if you want to make a share for your presentation,
I'll make a
click
screenshot
on.
and share it with them.
Okay.
Okay, okay. So this window show us the nodal analysis task. We choose the nodal analysis level and both the outlet pressure, which is the well flowing pressure here, which in our exercise 250. We click the run button and 62 stock tank barrel per day flow rate. And what we can notice in here, the bottom hole flowing pressure at this operating point is very high. So some sort of artificial lift need to be installed and designed first, then installed in this one. So we will get a flow rate naturally from this well at the given conditions. We will get a flow rate of 63 per day at a bottom hole flowing pressure at the intersection point is 3,297.6 psi at the bottom hole with reference to the mid berth depth. That's all from my side, and the share for us on.
Thank you, Engineer Abdullah, for this wonderful, amazing presentation. I did enjoy